Hello everyone. So today we are going to discuss one more application of visible light communication in vehicular to vehicular communication or automotive applications. Last time we had discussed about Wi-Fi coexistence. So today we are going to discuss how VLC can be used in vehicle to vehicle transmission, and also we will have one simulation study later by the TA of this course, who will be presenting a simulation study on vehicle to vehicle transmission. So let's begin. So what are the benefits of vehicular to vehicular communication? First of all, it will improve road safety, meaning there will be fewer number of accidents or injuries happening on the road if two vehicles are able to communicate with each other. It also helps in improving the efficiency of the transport system, so which indirectly reduces carbon dioxide emission, because you are not stranded in traffic jam, so you're not emitting unnecessary carbon dioxide from the vehicle. So it basically improves the overall efficiency of the transportation system. Intelligent Transport System, ITS, gives real-time access to the relevant traffic information, which actually helps in reducing traffic jams. You can find out some alternative routes. So these are some of the advantages of vehicle-to-vehicle communications. If all vehicles, they communicate with each other, or at least the vehicles which are in the vicinity of that particular vehicle, so it will result in some of these benefits which I have just discussed. So basically, increasing the efficiency of the transportation system will help save time. You are not stuck in a jam, for example. It will save money. You don't necessarily burn fuel, and it will reduce CO2 emission or reduce pollution. So vehicle to vehicle communication is actually, it's not limited to V2V now. The recent standards define this as V2X, where the X could be a vehicle, could be a pedestrian, or could be the network, or could be infrastructure. So V2X basically is vehicle to vehicle, vehicle to pedestrian, or vehicle to network, or vehicle to infrastructure, which would be a traffic light or the road light, or any kind of infrastructure. So this is a pictorial view of V2X, wherein you have V2V communication. Basically, it is avoiding collision, and it has safety systems built into it. And then you have vehicle to pedestrian, safety alerts to the cyclist or the pedestrian. And then you have vehicle to network, so you get real-time information of the traffic, routing, and the information is processed in the cloud. And then accordingly, appropriate decisions are taken. And then vehicle to infrastructure, traffic signal, for example, timing of traffic signal, priority, which vehicle should be given priority. So all those things are covered under these applications. So it is no longer V2V, it is V2X. This is a bigger picture of how this information is processed at different levels in the network. So if I divide the whole network into three main areas: remote access network, core network, and this is a service domain. So all the information which is collected here in vehicle to vehicle communication, some are processed in this layer itself by the V2X application server. Some of the information through the RAN is given to the core network, and some of the information is processed in the RAN network through this V2X application server. And then there is some processing which is happening at the cloud level, which is somewhere here. So the information which is generated here in the road, vehicle to vehicle or vehicle to infrastructure with traffic lights through the remote area network, which consists of E-Node Bs and LTE systems, is transported to core network, which has these entities, and then it goes to a cloud application server. So depending upon the urgency or depending upon the latency requirement for different applications which are there in V2X communication, they are processed either at core level or at the in the layer where it is on the road itself, or at the edge, which is application server located in the remote access network or in the cloud. So let us try to understand what are the different requirements for safety alert or safety services. So basically we can basically classify, we are not dealing with currently with V2N or other types of V2X services, but let us focus on mainly V2V and V2I, because we want to explore how visible light communication can be used for V2V communication and V2I or I2V communication. So I here stands for infrastructure. So these are some of the services: collision warning, for example, or blind spot, or lane change, or emergency electronic brake lights, left turn, and then there are V2I, reduced speed, curve speed warning, or stop sign violation, stop sign gap assistance, traffic signal violation warning. So these are some of the applications of V2I. And this LA actually gives what kind of latency is needed. That is, what is the maximum allowed latency. So this is maximum allowed latency. You need to process this information within this time. And this RM actually tells you what is the maximum range required for communication. Maximum range required for communication. So for example, take an example, collision warning. For example, you require a allowed latency of the order of 20 millisecond. And within 50 meters of distance, you should be able to communicate to avoid this collision. So if you see this table for different safety alert or services, you require on an average latency 100 millisecond in most cases, but there are exceptions where you require even low latency, 20 millisecond. And the ranges is of the order of 300 meters. So you should be able to communicate at a distance of 300 meters from one vehicle to another vehicle. And you require high reliability, that is high packet delivery of the order of 5 nines. That kind of reliability is expected in vehicle-to-vehicle communication system. And so these are some of the broad requirements for safety applications in terms of maximum allowed latency and maximum range required for communication and the reliability figures. There are now advanced services which are actually part of 5G, beyond 5G and 6G applications, where these some more applications are covered under intelligent transport system. One of them is vehicle platooning, where you have tightly coordinated train with reduced inter-vehicle distance. And this green vehicle, for example, is able to communicate with the second one, this communicates with the third one, and so on and so forth. So the distance between them is reduced, and all the movement is coordinated. So this is one example which is part of beyond 5G or 6G requirements, beyond 5G and 6G requirements. Or you have remote driving, remote control of vehicle by a human operator or by a cloud-based applications, which is an example of V2N application. The other application or use case is in advanced driving, where you require high bandwidth to support bus transmission of large quantity of data. So you are talking in terms of hundreds of megabits of 100 megabits per second of transport of data, and the latency requirement is further reduced for some certain applications, which is of the order of 10 millisecond. And then the reliability is 4 nines or 5 nines. That is a requirement. The other area, your use case is use of extended sensors. So you have more than one sensor, so that you get a complete picture of the road around you, about the pedestrians, about the vehicles in front of you, about the vehicles which are behind you, or some of the vehicles which you cannot see with your eye. You are able to get a picture of that vehicle onto your dashboard by use of extended sensors. So these are some advanced applications, platooning or remote driving or advanced driving or extended sensors, which are becoming part of beyond 5G, 6G applications. So inter-vehicle distance for different conditions. In a jam, the average distance is less than 30 meters because, see, you have to design a system based on certain requirements. We have studied what is the latency requirement, what is the communication distance, what kind of safety services are required, and what are different latency and communication requirement for those safety applications. And also we need to understand what is a average inter-vehicle distance in different traffic conditions. So traffic jam, it is 35 meters, less than 35 meter. For example, rural it is greater than 160 meters. So the distances are of the order of 160 or 200 meters, of that order. So one has to design a system, based on all these requirements. And also how the vehicle speed and the corresponding safety distance is related. So suppose this is, speed of the vehicle. If the speed of the vehicle is very large, then you require, more safety distance. So this particular curve, this blue curve, is actually a safety distance curve. Safety distance. So higher the speed, you require higher safety distance. And then the another curve is, the angle versus the speed of the vehicle. So if this vehicle, for example, this vehicle is, in line with the other vehicle, that means theta v is tending to 0, then you require some safety distance. And if this vehicle is little away where theta v has some finite value, it requires a different safety distance. So this particular green curve basically tells you about the angle part. So one has to see the combination of velocity, safety distance, and the angle in order to decide what is a safe distance for communication. So the requirements in summary for vehicle-to-vehicle transmission, which is part of 5G and 6G, that I require very low end-to-end latency. This is of the order of below 5 millisecond. Very high reliability of the order of 5 nines, 99.999. And the vehicle may be moving at a speed of 150 kilometers per hour. And your solution should work for high vehicular density, which is 500 vehicles per kilometer square on highway, or 1000 vehicles per kilometer for suburban applications to support wide range of V2X services. And also you require positioning. You should be able to position the vehicles around you to accuracy of about 30 centimeters. And when it comes to a vulnerable road user, it should be of the order of 10 centimeters. So the positioning accuracy requirement is of the order of few tens of centimeters. So these are the broad summaries which is required for V2X communication. So vehicle-to-vehicle communication, there are different possibilities. You can have DSRC, which is a current technology being used, which is actually dedicated short range communication. We have a standard for this DSRC, The other option could be your cellular, for example, LTE. That's the standard for vehicular communication. You use LTE framework or LTE network for communication between two vehicles. Wi-Fi was considered one of the solutions for vehicle to vehicle, but there are issues related to Wi-Fi. The one which we are going to explore is visible light communication system using headlamp of the traffic or a headlamp of the automobile or the vehicle, which will communicate with the other vehicle where you have the receiver, or the tail light could be a transmitter which will communicate with the other vehicle. The other option is millimeter wave, which is not currently explored much. And in future, there can be some other technology where you have, a lot of sensors around the vehicle. So we don't know about this technology. So there can be more options later. So let us see, we will, in this lecture, we are going to discuss about visible light communication. And also I'll explain what are the issues with the existing technology, which is RF based, which has a standard, which is part of the standard, which is DSRC, dedicated short range communication. So, and this is the standard IEEE 802.11p DSRC standard. So the problem in DSRC is that when the number of vehicles increase, then there is a channel congestion. And the message generation rate and the transmission range is reduced. So this congestion, channel congestion, whenever you have more number of vehicles, it will cause, broadcasting storm. Every vehicle will, start broadcasting, and this will result into a mutual interference. And also, because if there are more number of vehicles, the topology is dynamic, it is changing with time. So the packets may not be, the delivery of the packets may not be successful. So it will come back, and which will result into delays and improper packet delivery. And this quality of the channel changes randomly because the channel is a function of time and what is the topology around you. So it is very, very difficult to predict the quality of the channel. It is unlike, in indoor communication where the channel is deterministic. Here the channel changes randomly. So prediction is very difficult. And each node vehicle, because each vehicle is a node here, so they create interference that cover an area wider than the covered communication range. So that is a node which is a source of interference for the two vehicles which are communicating. And it uses CSMA-CA protocol, but when you have high traffic density, the efficiency of CSMA-CA actually gets reduced, and it reaches almost efficiency of LOA, which is not an efficient protocol. And there will be issues because there are some services which require 20 millisecond of latency, which cannot be met by DSRC. Even if the latency requirements are met or satisfied, the reliability requirements are difficult to meet because there are some external collisions are happening. There could be an issue of hidden node. There may be some vehicle which is not accessible to any other vehicle, so you don't get picture of that particular vehicle. So a problem of hidden node is a problem which needs to be tackled. Another issue is Doppler spread. When suppose you are using OFDM kind of transmission, then if the vehicles are moving at high speed, it will result into Doppler spread, and those subscribers, they will get, the orthogonality between the subcarriers will not be maintained because the Doppler spread will widen the spectrum. So this is another problem with DSRC. for example, in OFDM transmission, because if you are interested in high bit rate transmission, then one has to use some advanced modulation techniques. These subcarrier are orthogonal in OFDM, but because of this Doppler spread, they may not be orthogonal, which will degrade the performance of the system. And then rich multipath environment, which will result into our delay spread. So these are the issues with the current DSRC technology, IEEE 802.11p. So DSRC is affected by traffic densities, non-line of sight, and high velocities. So these factors will reduce the total communication range, cause numerous collisions, and increase the delays and reduce the overall reliability. So now let us see another mode of communication between vehicle to vehicle. So here we will discuss using light, how the system performs if you use the headlight and the tail lights of the vehicle. So the main purpose of the headlight is, illuminating the road, or the tail light just to tell your other vehicle about your position. So they have different purpose, but we want to exploit this head and tail light, the infrastructure which is already there in the car, for communications. So this is what we want to explore here. So visible light communication, as we have seen in previous lectures, it has limitations. The distance is of the order of 100 meters, although some experiments have been done greater than 200 meters. And we also require line of sight if you are communicating with the other vehicles. So there has to be a line of sight. But anyway, the researchers also have, given solutions where some sort of mobility can be met. So suppose this is a vehicle here, another vehicle here. So normally you require a LOS. But using some techniques, if the vehicle moves here or vehicle moves here, even then the communication can take place. But these are still some of the limitations: the communication range and the stringent LOS communication affecting the mobility. The advantages are that huge bandwidth, in the sense it's light, you have huge bandwidth, and this is unlicensed. Unlike RF solution or LTE solution or any other millimeter wave, for example, in future, they require licensed spectrum. So it's, that part of the spectrum is regulated. One has to pay for that spectrum, whereas in light it is unlicensed. Since it is a line of sight technology, so relatively free from mutual interference, although there will be some light coming from some other vehicle which are surrounding that particular vehicle, but that amplitude is quite low. So relatively free from mutual interferences and relatively free from multipath, because it is essentially a line of sight technology. So the multipath is rather, the amplitude of the multipath is rather less here. And this is a ubiquitous technology. That means all the lamps, the LED lamps and the tail lights, they are already part of the vehicle, so already integrated in the vehicle. So these are some of the advantages of visible light communication. So the basic structure of a visible light communication system is same as we have studied in the earlier lectures. So you have a transmitter here which uses a LED, and this is optical wireless transmission, optical wireless communication. And you have interference coming from light sources, from sun, from rain, or from cloud, from fog. So there are environmental conditions which will actually affect the communication distance. And then you have some sort of filter, some optics mechanism, and then you have the photodiode, you amplifier, do some signal reconstruction and signal processing, you get your data back. So this is the receiver part, which includes the optics as well. And this is the transmitter part. It may also have some optics so that it meets both your requirement of illuminating the road as well as the communication. and it is impaired by these noise. These are the noise in the system. So these are the examples of LED which will be used in vehicle-to-vehicle communication and vehicle-to-infrastructure communication. So you see some signs here, road signs, traffic lights, headlights, the tail lights, the direction signs, turn sign, things like that. They're all LEDs. So these are the LED objects which are actually the transmitter, which will be used for communication, for both vehicle-to-vehicle communication and vehicle-to-infrastructure communication. So when you characterize a vehicle-to-vehicle communication system, so there are three important quantities which need to be calculated or which needs to be investigated. One is average link duration. What is the average time the two vehicles are communicating with each other? Is it in millisecond? Is it in second? So that we will see. So that is the average link duration, the time during which the two vehicles are communicating. And what is the link throughput and bit error rate performance? What is the throughput you can get and what is the error performance? The third is channel time variation or coherence time. When you are considering vehicle light as the communication medium between two vehicles, so your channel is almost constant for how much time, which is actually called as the coherence time. This has implications on estimation because you have to estimate the channel and accordingly you have to retune your equalizers. So this takes time. If you're doing it frequently estimation, it will basically involve some overhead and it will increase your throughput. So we want estimation to happen in a longer time, or we want the coherence time to be large, right? So which actually will reduce the handover and effectively improve your throughput and BR performance. So these are the three quantities which are important if you are studying vehicular-to-vehicular communication link. The average link duration and the link throughput, bit error rate performance, and what is the channel time variation, coherence time of the channel. Other requirements, they include standard models or their mathematical models for car headlamp optical beam, which actually originally is defined for illuminating the road, not for communication. And it is not symmetrical. It has asymmetrical, radiation emission, so that, it does not affect the driver which is coming from the other direction, and it lights up the road in the near field and the far field. So you have two types of headlamps which basically illuminates the road. So this is we need to understand this optical beam pattern. We need to model this optical beam pattern, which can be taken from standard cars. So there are some standards for meeting this optical beam pattern. And then we need to model the noise sources, which is coming from sunlight or ambient light. And we also need to model the road surface of the light, because if the road is wet, and these are the two cars, for example, and this is the road, for example. So if the road is wet, how much light gets reflected from here, reaches here. I mean, there is line of sight anyway, but there is a component which is coming from the road also. If the road is dry or if there is snow, So the light behaves differently in different road conditions. So one needs to see the influence of road surface on the light and weather conditions. So for example, if it is raining, then the light will get attenuated. If there is a fog or rain, light will get attenuated. So one has to model this as well. So these are the other requirements which have to be modeled in order to find out what is the average link duration and what is the link throughput and what is the typical coherence time. So the noise and interference in DSRC, which is dedicated short range communication, which is RF based, and VLC is listed here. So you have thermal noise of the order of minus 104 dBm at 300 degree Kelvin, and the bandwidth is 10 megahertz. Then there is a noise which is coming because of inter-carrier interference. As I mentioned earlier, if the transmission is using OFDM, then different subcarriers, they may interfere because of Doppler effect, and the orthogonality will be lost, and this will result into some sort of inter-carrier interference, inter-subcarrier interference, and which will degrade the performance of the communication. High power interference from adjacent channels. So this may also be an issue in vehicle-to-vehicle communication. That is the interference coming from the adjacent channel. And interference due to imperfect receive filters. When you are sensing your OFDM signals, there may be some drift because of Doppler spread or this local oscillator getting shifted. So your filter may not work optimally. So there may be interference due to imperfect receive filters, and then also interference arising from the random channel access, which is a protocol between vehicle-to-vehicle communication. In VLC, there is a thermal noise and short noise because this is coming because of the detection process. And also the short noise is generated if you have sunlight and other sources of light. It adds to the short noise. The solar radiation, they happen to fall in the visible range. So this is also going to contribute to the noise in the system. Then artificial light, which is not from the headlight, any light other than the headlight and the receiver, that will contribute to noise, so which is artificial light interference. So one has to handle with care these different types of noise which are getting generated in DSRC and visible light communication. So in short, the difference between a visible light communication, DSRC, is it is line of sight, it is a broadcasting, which is the RF technology. People have demonstrated about greater than 400 megabits per second, whereas in DSRC, as per the specifications, 27 megabits per second. This is the frequency of the visible range, and this is the frequency of the DSRC, 5.85 to 5.925 gigahertz. There is no license required here. You require a license for this RF. The mobility is very low to medium because essentially it is a line of sight technology, but it can support little mobility. And either the mobility is high in this case. Coverage area is short range and narrow of the order of few hundreds of meters. This could be a kilometer, for example, 1 kilometer. Security, this being a line of sight, security comparatively higher as compared to RF, because if the LOS is blocked, you don't get any signal and you can get some alarm. So security is high in VLC, it is low here. The cost is low in the sense the LEDs are already inbuilt into the car, so there is no new infrastructure which is to be installed. So the cost relatively is low, whereas DSRC is very, very high because you have to put DSRC transmitters and receivers at regular intervals along the road. Complexity is low because designing a transmitter or a receiver for a visible light communication is not very complex, whereas the complexity of DSRC designing transmitter receiver is quite high. So at no point I want to say that VLC will replace DSRC. VLC also has some limitations. DSRC has some limitations. So it is finally a combination of these two technologies which will be a good solution, which will actually improve the performance of the communication. So places where DSRC is not giving good results, one can use VLC. Where VLC is not giving good results, one can use DSRC. So these are two complementary technologies. So VLC is not going to replace DSRC. So the reliability of DSRC is questionable because the reasons which I have mentioned. Is actually suitable for low traffic densities and for long range communication. VLC is for lower latencies, gives you high reliability, although the communication range is limited. So this is what I want to impress upon, that DSRC and VLC are complementary technologies. And the integration of the two can increase the overall reliability. For that matter, any other RF technology, not necessarily DSRC. So if we consider a typical V2V environment, you will see that while analyzing this vehicle-to-vehicle communication, you need to consider interference coming from other sources. The other sources could be the cars, which are different from the cars which are communicating. There could be reflection coming from roadside trees and buildings or some structures. The radiation pattern of the headlight, actually again it is shown here as symmetric, but it is not symmetric. It has, asymmetric pattern with different power levels depending upon where you monitor the power. So it has a symmetrical pattern which is designed actually for road safety and for illuminating the road during night conditions. And then ground conditions, what is the surface of the ground or the road, what is the reflection coefficient of the road, whether it is diffuse or it is scattered, or that depends on the quality of the road. And then weather conditions, because light communication will be impacted by the weather conditions. So basic VLC to VLC communication is designed. If you see here, there is a LOS you see here, and this is the part which is non-line of sight, which is reflected from the source. And then this is the interference part coming from a different vehicle. And this is the low beam pattern. This is the angle this side. So this is the low beam pattern. So the car actually has high beam and low beam. So this is a typical low beam pattern. The high beam is also similar to this. Only thing, it eliminates a longer distance of the road. So headlamp beams, road surface reflection, and interference from other cars, and the ambient noise one needs to consider while analyzing a vehicular-to-vehicular communication system. Now let us try to understand a VLC-based V2V model. So suppose you have a LED here, the headlamp here. This is the car headlamp, for example. And this is a road surface. And let us consider a small area DS on the road. So this is this solid angle which is getting lighted up here because of the headlamp of the vehicle, and let us denote this as d omega. This solid angle is d omega, and this distance from headlamp to the surface is, say, d, and let us draw a normal here, and this angle which the ray makes, the LOS, this is LOS, which makes with the normal is, say, gamma, and this is area ds. So if I calculate illuminance E, this will be equal to d capital phi over ds, where phi is the luminous flux. This These things we have discussed during the initial part of the course, where this luminance, lumen flux, candela, everything was defined. Luminous flux, and ds is the area of the road surface. Area of the road surface. And so the luminance E is d phi by ds. So this can be written as d phi over d omega into d omega over ds. And this d phi over d omega is nothing but I theta 1 theta 2 d omega over ds, where this I theta 1 theta 2 is the luminous intensity. This is a definition of luminous intensity, d capital phi over ds, luminous intensity. And theta 1 theta 2 are the horizontal and vertical angles with respect to axis of the headlamp. So d omega by ds. So this will become I theta 1 theta 2 into cos gamma over d square. So this is the luminous intensity. The units is in candela. This is in candela. These units are in candela. CD is given by cos omega by d square. So this is the luminance E happening in an area ds. So this is how you will find the luminance on the road surface area ds. How do you model a road surface? Now, there can be different types of road surface. So what happens actually if the light is falling from the headlamp onto the road surface, it suffers a diffraction. The light goes in different angles. And this typical angle is actually phi, which is not constant. It is changing. So this is the input light. So let us assume the source is Lambertian, which is not a good approximation, but for simplicity, let us assume the source is Lambertian with Lambertian parameter as 1. So the R phi, which is the luminance coefficient for the range of angles, is given by rho cos phi divided by pi. This is the diffuse reflection constant, which is actually function of road surface. So this is how broadly, road surface can be modeled. So R phi, which is luminous coefficient, which is a function of phi. The scattering angle here is given by rho. Rho is diffuse reflection coefficient into cos phi, this angle phi, which these rays are making with the incident light, divided by pi. So this is a very simplistic modeling of road surface. And phi, we can call this as polar angle of the scattered light. Now let us see a VLC channel for V2V communication. How does the channel behave? So let us draw a diagram where you have the car headlamp here. This is a car headlamp, and this is the road surface. And say suppose this is your receiver here. This is my receiver. I call this as point B. And this is, say, area DS I have taken on the road, and I call this point as A, for example. So there will be a line of sight. This is line of sight. And this is R. So I'm considering, for example, this is right side headlamp, RSH. Right side headlamp. Right. I'm just considering right now only right side headlamp. So this will be I, RSH, and this is a function of two angles, which are horizontal and vertical angle with respect to the axis of the car lamp. I call them, let us see, are rather theta 3 and theta 4. The other one is the reflection, non-line of sight. This is non-line of sight. And also, so this will reach to the receiver here. So let us draw a normal here. So this angle which the line of sight makes with the normal here represent as psi LOS, and the other angle which the non-line of sight makes, let us call this as psi NLOS. And let us make a normal here, and this angle which the non-line of sight makes with the normal, let us call this as gamma A, and the other angle which the on this side, let us call this as phi A. And this is the point A, this is the point B. And this distance is from the right side headlamp to point A, and this distance is from A to the receiver. And this is IRSH, and now let us write, so there, this luminance IRSH, it will be function of theta 1 and theta 2. This was function of theta 3 and theta 4. So as I mentioned, theta 1, these thetas are the horizontal and vertical angle with respect to the axis of the lamp. So the luminance which is E R right side headlamp at A is given by I RSH which is function of theta 1 and theta 2 sine gamma A divided by D square, the distance, that is RSH minus A. This is luminance at point A. Now the vertical radiant flux let us call as a dp rsh a. That is a vertical radiant flux which is coming from the surface of the road. Let us call as dp, because we are considering only small area ds, from right side headlamp and from position A, is given by E RSHA into ds divided by LER, where LER is important here. LER is luminous efficiency of radiation. So normally the LEDs which are used in the cars, they are phosphorus coated LED, and actually the LED is emitting blue light, but it phosphorus coated, it has yellow light. So when they mixed up, it gives you white light. So that is a normal LED which is used in the car. So, and they have certain LER value. So they have typically of the order of 250 lumens per watt. I mean, these are values of a good per watt, good LED. So this is how you measure LER, lumens per watt. So luminous efficiency of radiation. So this is vertical radiant flux. So this will be equal to, we have to put this ERSH A from the earlier equation, say this equation number A, we put this value. So what we get is R right side lamp theta 1 theta 2 sine gamma A divided by LER d square RSH minus A into ds. So this is the vertical radiant flux. Now receipt power at B. Receipt power at B, that is at the receiver, will be, and this is, we are considering currently the non-line of sight component. So let us designate this as dP coming from the surface ds at the receiver from the right side headlamp, and we are considering non-line of sight, is equal to dP, that is a vertical radiant flux, dP RSH A into area of the receiver Rx into R phi A, this is the reflection or the scattering part, phi A, cos psi NLOS, and divided by the distance, and the distance is d square RSH A. So this will be d square, this distance will be A to Rx. So we are talking about this distance. So this is the receipt power because of the vertical radiant flux from area ds on the road surface. So where this R phi A, as we have discussed earlier, is rho over pi cos phi A because of the scattering. So this is how we had modeled. You know, the light is falling here, light is falling like this, and it is getting scattered, and this angle is actually phi. So this is given by this coefficient R phi A is equal to rho, which is a diffuse constant or reflectivity constant divided by pi into cos phi A, and this is a function of phi A. So the total power received PRX from the right side headlamp, because of NLOS, this is a total power now, will be integrated over the total area which is getting illuminated from the headlamp. So this will be integrated over the surface S, and this is dP, Rx, RSH, NLOS into ds. And this will be when psi NLOS is less than psi. So, and this is only valid when the angle of psi NLOS is between 0 and psi, because that is the FOV of the receiver. Anything away will not be going to the receiver, hence will not be counted. And this is 0 if your angle psi is greater than psi non-linear sight. So this is the component from the non-linear sight. Similarly, we can calculate the component which is coming from the line of sight, that is PRX from the right side lamp LOS. So this will be given as I RSH. Now this is a function of theta 3 and theta 4, because these are the horizontal and vertical angles with respect to the axis of the headlamp, into divided by LER, and this distance is d square RSH Rx. This is this distance into the receiver area ARX into cos psi LOS. And when psi LOS is between this angle, only this value, otherwise it is 0 otherwise. If psi is greater than psi LOS. So what we get is the total power both from line of sight component, this is this component and this component, suppose this is say A, this is say B, the total power is actually A plus B. And this we have done only for the right side headlamp, but you need to include the power which is coming from the left headlamp. So the total power, this is actually from the right side headlamp. So the total power which, so this is only from RSH. So the total power which is both from RSH and LSH. So this is RSH, right side, and left side headlamp will give P RX minus RSH plus P RX minus LSH. So this is the total power you get onto the receiver from left hand and right side lamps. So this is how one has to calculate the power which is getting received at the receiver. Sometimes one can use MIMO to increase the effective throughput. So this also we have studied MIMO in earlier classes. So normally you have two types of sources, the right side and the head side, and similarly you can have two receiver, onto the two set of PDs onto the receiver. So the model will something become like this. So this is, for example, your transmitter. So you will convert, say for example, serial to parallel. You get some X1 here, X2 here, and this can go from say left side headlamp. This can go from right side headlamp, and then you have two receivers. This is say LSR, that is light side receiver. This is left side receiver. This is right side receiver, and this is the channel actually. So the MIMO channel will be, light will go here as well as here. It will go here as well as here, and these, they have channel coefficient as Hij. So this is, for example, H11, this will be H12, this will be H21, this will be H22, and then you have Y1 here, this is Y2 here, and then you use some sort of equalizer. So if this is H here, and it is a 2 cross 2 matrix, so you can always take an inverse. So if you have equalizer which has this characteristic H minus 1, then what you get is, and this is some serial to serial, and this is your received data. So this is your estimate here, X1 estimate, this is X2 estimate, which is converted into serial, and you get the received data. And HIG is the, so if you see the whole model, this is Y is equal to Hx plus N. We have these N are vectors and H is a matrix. So, and Y is, Y vector is given by Y1 or Y2 transpose, and X vector is given by X1, X2 transpose, and H is given by, there will be, it's a 2 cross 2 matrix, so it will be H11, H12, H21, H22, and the noise vector is given by N1 and N2 transpose. So this is how you can model, and one, in order to take the inverse, H inverse, it has to be a full rank matrix. So one has to ensure that we get a full rank matrix, only then inverse is possible. So using this, one can get better throughput or better performance in the system. So this is how MIMO principles can be used in vehicle-to-vehicle communication or car-to-car communication. So as we discussed, the noise in the VLC system, because ultimately you have to calculate signal-to-noise ratio. So noise sources are background solar radiation or artificial light during night, and you have the total noise is short and thermal noise. The short noise is given here, where this is the responsivity, E is the electronic charge, this is the receipt power onto the receiver, receipt power, this is the background noise current, this is part of the, because of the short noise, because of the background noise current. And this is some noise bandwidth factor, noise bandwidth factor of the background noise. And BS is the bandwidth of the system. So this also we had discussed when we were discussing about the detector. It has short noise and thermal noise. So the expressions are given here for the short noise and thermal noise, which is actually dependent on the RL of that is the load resistance of the receiver. So characterization of V2V channel link is done as we had discussed. We need to find out what is the average link duration. What is the time, average time during which the two vehicles are communicating. So in a typical experiment, I am just sharing some results here. It is found, suppose this is your link duration, and this is could be in terms of seconds here, starting from say 10 seconds to 10 raised to power 3 seconds, and suppose I plot CCDF here, cumulative complementary distribution function, and this can be different for example non-urban scenario, where traffic density is not very high, or urban scenario where traffic density is very high. So if you plot this curve, the typical curve looks like something like this. CCDF value is say very low here, -4, and it is say 10 raised to power 0 here. So this is for example for non-urban environment, and if you plot similar for urban, this will be little less here. So this is for urban, because in urban the traffic density is more, there will be more vehicles, they will have more interference. So basically the average link duration will come down in urban environment, but it is of the order of about goes up to 10 to the power 3 seconds. And if you take a specific case at, for example, at red light intersection, at say for example red light intersection, then if I plot the same curve, so this is link duration here, and this is say again CCDF, cumulative complementary distribution function. So normal case is something like this, as we have drawn in the earlier curve. But at the red light interference, this will, all of a sudden it will start dropping here at some point, because during the red light, all the vehicles are, close by, and they are all sources of interference to the communicating vehicles. So it basically falls down sharply. So this is a specific case when the vehicle is at red light, then the average link duration actually gets reduced. Similarly, one can study by changing the FOV, field of view of the receiver, and plot the link duration versus CCDF for different field of views. So it will be, for example, this FOV here is say 60 degree. If I increase the FOV to 90 degree, the performance will little go down. This is FOV is equal to 90 degree. Because if you have the wide FOV, that means it is getting interference from in a larger area from different sources, different vehicles, which will actually increase the noise floor. So that is why you see the performance degrading when you increase the FOV of the system or FOV of the receiver as compared to smaller FOV. But if you have the smaller FOV, which is good from this particular aspect of link duration, but smaller FOV will require strict line of sight, communication. So you lose on the mobility part. So it's a trade-off between the two. So this is, some typical results for a vehicle-to-vehicle channel and link for link duration, average link duration. And if I see the coherence time, V2V VLC channel coherence time, and let me first plot a curve between, say, this is the coherence time or the time displacement. So this basically tells you the channel is how long the channel is constant, what is the duration in which the channel characteristics are same. Because this is very important, because you have to estimate the channel, and if you are doing frequent estimation, there is some overhead associated with the estimation, which decreases the throughput of the system or the BR performance of the system. So this is a tau. So this is something like this. Here it is again, let me call this as normalized auto correlation function, R tau. So this will be 0 to 1, this is normalized here. So there are two ways of defining coherence time. Either you use 90% correlation, that is, the channel has changed only by only 10%. The other is 50%, a broader definition, the channel has changed by 50%. So if you see the values at 90%, say this is a 0.9 and this is 0.5, so this will give me, this value of coherence time, whereas this will give me this value of coherence time. So the 90% coherence time is typically 33 millisecond. Whereas if you take the definition of 50% coherence time correlation, this is of the order of 460 millisecond. So the channel in the first case, when you take the 90% definition, is constant for 33 millisecond. Only after that you require estimation of the channel. And if you take a little loose definition, which is 50%, it is about 460 millisecond. But in the RF case, these values are in microsecond. So clearly, as far as coherence time is concerned, VLC is significantly better as compared to its RF counterpart, whereas the coherence time of the order of few tenths of millisecond as against microsecond in case of few tenths of microsecond in case of RF. But this is a case condition for a case when you are considering line of sight communication for these two examples. So this is very important. If you have a longer coherence time, the estimation requirement is relaxed. You require estimation, after a long interval, which actually reduces the overhead and increases your throughput. So finally, let us see the V2V VLC BR performance. So if I consider, for example, a simple scheme of on-off keying, the signal to noise ratio is given by sigma r p square where this is the responsivity of the photodetector, PR is the receipt power, and this is the noise, total noise in the system. And we know for OK, BR is given by Q function, it is defined by the Q function, which is nothing but root SNR, because if you see the first term is signal power divided by the noise power. And let me write here how you define the Qx, the Q function. It is x to infinity, 1 over root 2 pi e raised to power minus t squared t divided by t. So this is the Q function. So BR is given by Q of root SNR. And if you see, the Q is the gamma, the power received by the left side. Right side, let me write this as right side lamp plus R received by the left hand divided by sigma total. And if you plot, for example, the distance between two vehicles, and on this side if I plot BR, bit error rate, and start -6 on this side and say this is 10 raised to power 0, and this distance let us start at 50 and this may be 200. So what you get is something like this. So as your distance increases, because your receipt power is less, your BR performance goes down. So this is actually case of without MIMO. If you use MIMO, then there will be an improvement and your performance will be something like this. This is with MIMO, which I had discussed earlier. So this is a typical BR versus a distance between, so one can suppose this is 10 to the minus 3. So you can find out the distance, corresponding distance for these two cases. So this is about the BR performance. So we have seen, different parameters, the BR, we have seen the link duration, we have seen the coherence time. So these are the metrics which define vehicle-to-vehicle communication. So we see that VLC can play an important role in vehicle-to-vehicle communication, specifically if it is being done along with a RF counterpart, could be a LTV or DSRC. So you get increased performance if you use a hybrid system because they are complementary to each other. So we also have one of the simulation exercise planned, which we'll discuss in detail about vehicle-to-vehicle communication and how you can, simulate and, and draw these different metrics or the results. So this is another application of VLC which we have discussed today. Thank you very much.